Okay, let's dive right in. So there's homework due now, and we'll have one out this afternoon. And last time, this is an error, right? Last time we looked at this, a pi over 2a orbital, and we couldn't figure out why this one was the same phase as these three, and so this is correct. This center one should be shaded. Okay, so just a reminder, what we were looking at last time was this the notion that there was a combination between our linear combination of atomic orbitals between individual hydrogen atoms or species within a substance, and an overall oscillating function that is characteristic of that material. And so this combination then resulted in an overall wave function that could be described by that block function. So let's do one more practice on this. What would be the relative areas of these circles? A, B, C, D, and E. Could you do it really quickly? We know the period is what? Is pi over 4a. So then, root 2 over 2. U would be root 2 over 2. Right? Is everybody following that? That this is 1, this is root 2 over 2, this is 0.
That's not the size of the orbital saved, right?
That's right. Yeah, it's the relative. Yeah. Thank you. The area of the circle, which represents the relative bonding and non-bonding properties of those orbitals. Yeah. Okay. Good. And then we looked at a band diagram briefly, and how the band diagram approximates or plots the relative energy relative to the energy of an individual constituent atom, in this case hydrogen, as a function of these different frequencies, okay? And that this distance is known as the band width, 4 times this beta, where the beta is a drop in energy relative to the energy of the constituent electron, or constituent atom, so negative 13 electron volts for hydrogen, okay? And that this line then could then be represented in this equation, where this energy at any k is a function of the energy of the source material times the bond energy between 2 neighboring 1s orbitals, this cosine term from the block function, and the Ka is then our whatever we're putting into the equation. So energy as a function of these Ks. Okay. So when at this point this entire term drops to 0, right? Because pi over 2, the cosine of pi over 2 is 0, right? Okay. So if you read the text, she goes on and shows a couple other examples of how this changes as a function of bond length. So if you could kind of do some hypothetical experiments to adjust the bond length between these different hydrogens, how would your band width change, right? This overall, the point here minus the point here. Okay, and so the solid curve is a shorter bond length. The dash curved is a longer bond length. And so as the band width depends on the bonding interaction, as the adjacent atoms become farther apart, they start to behave more like individual atoms, and hence that's why this dotted curve is all points on there are closer to E sub naught, right? They're closer to your negative 13 keV or EV. Whereas when they're closer together, the solid curve, you get more of a distribution because you have more states, Yeah.
Is there a function that relates this distance to the energy to the energy width?
This band, no, well, this is related to the bond energy. So, yeah, I don't know what that is, but there would be a separate relationship between the energy of that bond and the bond width. Yeah. Okay. So yeah, strong sigma interactions between 1s orbitals result in a larger bandwidth because you get more coupling. Yep.
Wait, so bandwidth or bond length?
Both. So strong pi interactions, which is what you're getting in a short, did I say pi? Strong sigma interactions between 1s orbitals, which would be a short bond length, results in a large bandwidth. Bandwidth meaning the distance from there to there, your range of energies. Yeah. Okay. And so then to look at this comparing to our density of states, this is kind of confusing because this looks like our Fermi-Dirac distribution, but it's not, right? This is just looking at our same bandwidth plot and comparing it to our density of states, okay? And again, when we first constructed this, we showed that these are all of our bonding sigma orbitals, which are lowest in energy, right? So this makes sense that this point down here corresponds to our lowest energy on our density of states for linear hydrogen, okay? So what would this look like then if we changed our bond length? What would this look like for these two states? So if this is our 1.48, actually let's call it the 0.74. So where would the longer band length be? Tighten it up, right? Does that make sense? That it would be more like this. Again, because we're going closer to the concept of an individual 1s. And so that's what this looks like right here. As they become farther apart, you tighten it up closer towards the center. Okay? Okay, so now we're going to move more into, yes?
Does this mean that the conductor band is anti-bonding orbitals?
The conducting band is anti-bonding orbitals. There can be some, yeah, and that's kind of what the block function was looking at, is the contribution of where do you have bonding and non-bonding orbitals in your occupied orbitals, right? I mean, so yes, do you have some, I mean, it's not all bonding that are occupied orbitals. Yes?
Doesn't that kind of follow from our exploration of molecular orbital theory, where the higher energy states tend to be non-bonding? So we'd expect anything that's in a higher energy state would be non-bonding, or in the new nomenclature, valence.
Yes. Yeah. Yeah. Okay. So just we're going to start to talk about carbon as a conductor, and so you know from your own experience, your own life, that this is what metals look like, but that metals electrons are essentially delocalized over the entire piece of metal, right? So when you think about carbon or plastics, I mean, that's kind of what we're talking about today, is plastics. If your intuition is that they're not really, these electrons are not delocalized, right? And that they're confined to the individual atoms that make up the plastics, but in certain situations that's not the case. So conducting polymers are characterized by a conjugated system of pi orbitals alternating single and multiple bonds. So the example we're going to look at, and kind of the gold standard example, is polyacetylene. So what do we mean by conjugated? Just to remind you, if you haven't taken organic, conjugated system is connected p orbitals with delocalized electrons. So alternating double bond, single bond, double bond, single bond. So these two would be conjugated with each other, right? And this situation would not be, right? And so kind of so this situation then would be conjugated, right? Because these are alternating. But if you had something like this, that would not be conjugated, right? And that's what this means then, is that this is the same thing as right? That this representation is completely flexible over and delocalized over the entire, in this case, benzene ring, okay? So this ability to have multiple conformations in the same energy state lowers the energy of the molecule, increases its stability, okay? So you essentially get this overlap of p orbitals across this intervening sigma bond, okay? So despite the fact that these pi electrons are not directly adjacent to each other, they can couple. They can transfer electrons back and forth through these adjacent pi bonds, okay? So this pi electron then becomes delocalized, okay? So polyacetylene is a conjugated polymer composed of repeating ethylene units that has this exact same kind of conformation. So these next few slides are kind of going towards is looking at, so previously we looked at how nano has unique characteristics relative to something that's big, right? We walked from a 3D system down to a 2D to a 1D. And now we're going to start from a molecule and show how nano hits another kind of sweet spot. And that, so these kinds of long polymers that adopt a nanoscale conformation, or graphene, have special electronic properties that just a single molecule doesn't, right? Like ethylene or butadiene, or these smaller molecules can't be semiconducting. But when we move it up to onto a nanoscale regime, we can hit this semiconducting kind of property, okay? So kind of the inverse property of showing the attributes of nano, but now relative to a bulk system, now relative to a molecule, okay? So how do we get these conjugated systems? Again, so sigma bonds and pi bonds, and these are just some cartoons that I liked, and so it's saying the same thing over and over again, where you have these p orbitals that have this electron, and because of this alternating system, you can have conductivity flow through this, okay? So this is the same thing as what I just drew right here. But what does that look like from like molecular orbital theory? Okay, so if we think about a monomer, a methyl radical, so CH3 with an electron, okay? So this is going to be an overall carbanion, a negatively charged carbon, okay? So you would have a hydrogen, 3 hydrogens within these sigma bonds, right? And then you're going to have a p orbital that has 1 electron, right? Positive and negative nodes, right? Okay. So this unpaired electron or radical is in this atomic orbital perpendicular, okay? The pi atomic orbital has a radical in a lobe above and below the plane, okay? Probability at the always 0 at the nucleus, okay? So the elliptical and electronic properties of polyacetylene, all these polyenes, are due to this highest occupied molecular orbital, which here is obviously that one, right? These are going to be much lower in energy than this thing, which is like flipping out because it's all on its own. Okay? Yeah.
This is kind of from the last section. Like, what if you had like an alternating system, like triple, double, and single bond? Would it be even more delocalized then?
I don't think that. So if you did something like, but then you had that.
Yeah.
I don't think that's conjugated. Yeah, because this is it's like throwing a kink in the entire system. This has a very different resonance than the next one over, right? Like these two interactions are very different than I drew this wrong. No, I didn't. Are very different than this. So yeah, that's disrupted it.
Okay.
Yeah, it's no longer conjugated. I'm sure there are exceptions to that rule, but I think by and large that's a safe assumption. Okay.
Professor,
yeah.
In a conjugated chain, do we think of it sort of like a resonance structure where the double bonds aren't really between parts
yeah.
A and B and then C and D? They're just sort of 1.5 bonds all the way along.
That's why I included this cartoon, because I think it's kind of it's a decent approximation to what's kind of happening here. Yeah, where you can kind of think of these as becoming no longer unique to, this carbon or this carbon, but these, is it
similar to the two-dimensional conductivity we've seen something like graphene?
Similar, yeah, exactly, yeah.
What about alternating triple single? Would that be?
Triple single, boy, I don't know. That's a good point. So now you've changed the geometry. If somebody knows, I don't know. So, yeah. Oh yeah, sure you can make that. Right? But I think yeah, the geometry is going to be very different, because even within trans and cis acetylene, like when you have cis transacetylene, you don't have nearly the amount of conductivity because you essentially bend those orbitals back on themselves. Yeah.
Plus, to draw the resonance structure for this, you have to be moving two bonds at once.
That's a good point too. Yeah, did you catch that? To draw the resonance of this, you'd have to be moving two bonds as opposed to one. So I'll have to go back to my organic chemistry book, but I don't think that's how it works. Okay, so what if we now combine two of these into ethylene? So here, ethylene now is a pi conjugated system. So two methyl radicals come together, you lose a hydrogen, and each carbon has a pi electron orbital that overlaps, right, with each other because these carbons are close. So now you can form this pi bond, which we've seen before. Yeah?
So will the orbitals never be hybridized? Or this?
Well, what is the hybridization here?
Will there be four bonds?
There's going to be three sigmas per carbon, right? 1, 2, 3, and 1 pi. So that's going to be, yeah. But what's the hybridization of this? sp2. So this is hybridized. Yeah. Yeah.
Did you say that the vertical ones are like different energy?
Yes, they are definitely lower. They're definitely lower in energy, but that's because they're sigma sp2 hybridized, and this one is your pi orbital. Yep. Yeah.
In this the figure, the p orbitals, the pi, the electrons will be located with negative charge ones.
I mean, you're thinking about this in terms of node. Like, it's equally probable that they can be here or here, right? It's just that these are two different nodes of the same orbital, right?
So that isn't an anti-bond on the line?
Wait, I said that wrong. So, yeah, so you've got, I said that wrong. You can think of it as being an either node, an anti-bonding, and a bonding node. Thank you. Yeah. Okay, so what does this is kind of a weird way of looking at our molecular orbitals because we're only looking at the pi here, right? So what if now we're considering our two pi wave functions with the same sign to form a bonding molecular orbital? Okay, so now we have our pi highest occupied molecular orbital from atom A, same thing from atom B. Okay, so those are going to come together to form now a bonding pi A and B, anti-bonding pi A and B. Okay, it's just that you're going, right, this lone electron, this electron are now coming together to form this kind of pi bond, right? Okay, and in the bonding situation, there are no nodes because these are aligned, right? Whereas here they're flipped and therefore you have a node, higher energy, lowest unoccupied molecular orbital. Okay, yeah.
Notice you say when they're aligned, there's no node. So does that mean that electrons in anti-bonding orbitals that are both pointing in the same direction actually bond pretty easily?
Anti-bonding orbitals pointing in the same direction. I mean, you can also think about them being bonding, pointing in the same direction, pointing in the same direction.
Because it makes sense that when they're opposite, they're not matched together well.
But this makes sense, right?
Except for the name.
That this is bonding?
Oh, that's bonding. Oh, okay.
Yeah, yeah. So that's, yeah, our bonding, anti-bonding. Just like we did sigma, sigma star, this is pi, pi star. Yep. Okay. So what if now we moved it up to butadiene? So 1, 2, 3, 4 carbons. Okay. So now we're thinking about, in terms of these pi electrons, we can think about this as butadiene corresponding to the interaction between two ethylene subunits. Okay? So just like here, we were combining these two methyl radicals. Now this is coming here, and this is going there, right? So we're combining ethylene 1, ethylene 2 into butadiene. So as we start to fill up these pi orbitals, now we've filled up these two types of pi bonding orbitals. Okay? But what do the nodes start to look like? So here's ethylene 1, here's ethylene 2. These are your two bonding pi orbitals, but you get this node difference. And this node difference, this translates, this is a different representation of this double bond, single bond interaction. This is, they're showing these as being occupied. I mean, these are not, there are no electrons here. It's just showing what would this look like, right? What would the orientation of these orbitals look like in these higher orbital situations? These are where your electrons are, right? This is this, okay? So what do you think this corresponds that, like, as we keep adding these together, what do you think this does to our band gap?
It lowers the band gap.
Okay, why?
Because once you have a conjugated system, it's more stable because electrons flow in between, so it takes less energy.
Yes, and extending on that, as we add in all of these additional nodes, what's happening here that we don't have here, right? Or what is this doing to the energy of this system relative to this system.
It's all continually lower.
It's, well, lowering
Or at least it's collapsing. It's coming in closer
to,
to the middle of the.
yeah, right? So this is a higher energy system, right? So you're pulling this, your bottom is coming up just as your top is coming down, right? Because this definitely has more energy. This is more energetically disfavored than this. And as you add more and more and more of these things, you keep adding in more and more nodes to your occupied and unoccupied orbitals. Okay? So this is what the numbers actually look like. So 6.7 electron volts or 185 nanometers for ethylene, butadiene. Here we're at 3, and then when you get a polyacetylene system, you start to be below 3 electron volts. And so now we're in the range of a semiconductor, right? Because we're adding, not only are we pulling this up, we're kind of pulling that down. Okay? This was really helpful for understanding this. I really liked this page. Okay? So you want to see a practical application of this. So this was something that I did as a postdoc where we wanted to measure these free radicals. So superoxide, hydrogen peroxide, peroxynitrate, there's all kinds of these things, and they're very short-lived, but they're implicated in a whole bunch of bad things. And so I use this technique called photoacoustic imaging, where rather in regular ultrasound, it's sound in, echo, and sound back, right? In this technique, we do light in, sound out. So there's a very short light pulse, and the material absorbs the light. And when it absorbs the light, it heats. And when it heats, it swells, right? Thermal expansion. So we can detect then that pressure wave acoustically. So that's pretty cool because now we can start to have 680 nanometer sound, 780 nanometer sound, 880 nanometer sound. Yeah.
Does the sound output wavelength correlate in a direct way?
Nope. It's big and dumb and broad. And that's the problem with ultrasound is that you get these huge range of frequencies and the transducers are very broad. So I can't say I want to only listen to 21 megahertz. You're ending up looking at everything from like 10 to 30 megahertz. Okay? But if I'm only producing sound at one wavelength, then I can control that because I can do that sequentially. Okay? Yeah?
Random question. Why can you not look at bones? It might just be, I don't know if it's a...
Because it's hard to get light through bones, and B, it's hard to get high frequency. Yeah, you can get high frequency sound through bones, but not light. At least not a lot of like human skull. So we took this semiconducting polymer, and so, you know, of course, transacetylene is the textbook example, but you can imagine these kinds of conjugated systems being semiconducting polymers. And so you could imagine how we could tune the identity of these monomers to get a wavelength of interest, right? Where do we want it to absorb? Well, you can control that by picking the type of monomer and the length of your chain, right? So we created this polymer made out of, or excuse me, a nanoparticle made out of this semiconducting polymer. And the semiconducting polymer absorbed 700 nanometer light and produced photoacoustic signal, okay? Then we doped in this other thing that was specific to reactive oxygen species, okay? And it produced photoacoustic signal at 820, okay? When the ROS was there, the reactive oxygen species, it cleaved this, so this thing no longer produced photoacoustic signal. And we were only left with signal from the semiconducting polymer. Okay? Yeah. It cleaved I think it opened up that amine. I'm not exactly, I can't remember the exact mechanism, but it tweaked with this small molecule, not the semiconducting polymer. Yeah. So this thing was doped into the polymer, a small molecule doped in with the polymer and the nanoparticle. So in the absence of target, you had, we're calling this green, even though it's 700 nanometers. Green plus red equals yellow. When your thing was there, you only had green, right? So this is ratiometric imaging. Why do you think this is advantageous relative to just using this thing, right? If this is what's specific to our analyte, what we want to image, what's the point of even having this? What's the advantage that this kind of ratiometric approach might have? Yeah?
Can it give you better contrast for an idea of like how much concentration is in the
No, not necessarily contrast. What do you think?
So if you just have like a single signal, and if you have noise, you can't really tell what the signal is and what's the noise. But if you have two, you can cancel it out, so you can only tell which one.
That's a much closer response. The other issue too is that when you're trying to image through tissue, there's a ton of variation in what's between your target and between where your light goes in, right? So if there's differences in fat, in blood, in anything there, that's going to modulate how much light goes through that tissue to your target. But if you have this reference signal, you can constantly normalize it to your reference signal, right? So if I was only looking at this and my signal went down imaging here to here, is that because there's just simply less light that gets through here relative to here? Or is it because there's a real difference in the amount of reactive oxygen species? Well, by normalizing relative to this thing, I can control for that, right? Yeah. Oh, that is a phospholipid that we used to, I think, probably put some PEG or something on the surface. Just a stabilizer. We could, yeah. So then this is photoacoustic spectra. So photoacoustic signal as a function of wavelength in the presence of just the nanoparticle, hydrogen peroxide, or peroxynitrate. And so this signal comes down. We could look at different reactive oxygens, and we were selective for peroxynitrate and hypochlorite, and then went on and validated it in cells and animals. So, okay. So these conjugated polymers did win the Nobel Prize 2000 and have gone on to be used in all sorts of photovoltaics and stuff everywhere. Okay, so now we're going to move more into carbon-ish. Who could write out, do you guys learn this previously? Like, do you know how to draw and label these different carbons? Like, if I said, this carbon is 0, 0, show me carbon 5, 5. Could you do that? Okay, so that's a good thing to do on a Friday afternoon or Friday morning.
You played all night.
But then you got these long tubes sides.
That's extras. Can you pass those back? Everybody have one? Okay, so let's kind of pick an arbitrary. It is completely arbitrary because we're assuming that this thing goes on in every dimension for forever. So let's call this one 0, 0.
Did you just decide that?
I could have called this one 0, 0, this one 0, 0. It doesn't matter. I'm picking this one because it's on the lower left, and that's generally where the origin, we tend to think of the origin as being the lower left. So that's why I picked this one. Yeah. So this one, now we can still kind of think about it as x and this direction being y. So this one is going to be 1, 0. Okay. I wonder if there's any way to zoom. I can zoom. Oh no! We live in amazing times, I tell you. Don't let anybody get you pessimistic.
Maybe the autofocus would be better if you move the paper.
No, that's good. That's good.
Okay, so this one's 1, 0. So 2, 0, 3, 0, 4, 0, 5, 0, 6, 0.
Yeah. They're pretty big.
Okay, so that's our x direction. The confusing thing here is that in the y, this is not 1, 0. This is 1, 0. I'm sorry, 0, 1.
Wait, so what would the atom right above it be of 0, 0?
Oh, hang on. This one is going to be 0, 2.
Oh, I get it. We have non-orthogonal axes.
Thank you.
Yeah.
This one is 0, 3. This one's 0, 4. Okay, so if I was to then, I wonder if I have a red pen.
So if you were to choose the one right above it, it would be 1, comma.
So there's my x, and then my y. If you want to think about it as a y, is like that. So if this is 0, 3, then this is going to be 1, 3, 3, 3, oops, 2, 3, 3, 3. Four, 3. Similarly, this is going to be 1, 2, 2, 2. So if I was to then draw from 0, 0 to 0, 1, I'm sorry, 0, 0 to 1, 1 to 2, 2 to 3, 3, it would be like this.
We can't see when you're doing that.
So you're exactly right in that these are non-orthogonal axes. Yeah.
So what's the angle between X and Y? Is it just 60?
I think it's 60. Yeah.
Professor?
Yeah.
So the distance between like negative 1, 2, 0, 0.
Between, say that again?
Well, like distances wouldn't be the same.
That's right, yeah, yeah. Don't try to think about this as like a Cartesian system. The reason the people invented this approach is to kind of describe how do you then think about carbon nanotubes, because there's different kinds of carbon nanotubes. And even though you don't make carbon nanotubes by folding up graphene, a very common type of carbon nanotube is, so if this one is 4,4, this one is 5,5, would be to just talk about like a 5,5 carbon nanotube, which you would create by folding this 5,5 point back to the origin. Okay? Yes, right? So like fold it back on itself that way. Even though that is not how you make carbon nanotubes, but there's a way, it's how the community has kind of decided to characterize these things.
So what would, on that one or that 5,5 line, what would that intermediate value be? Would it be half-half?
Don't, yeah, half-half, or you do, it doesn't have an expression per se. Okay. Yeah, yeah. Yeah, exactly, because we're not labeling all of these atoms. Yeah.
The point of this isn't to be able to find an address for any particular atom. It's more about just finding.
It's more of a characterization system. Yeah.
You said pulling the 5,5 back.
Yes. Yeah.
How is it actually?
How would it would be by bonding that carbon to 0, or replacing the 0,0 carbon with this carbon.
You said that it's not actually formed by doing it, right? So how do you
We'll get there. But can you appreciate that how that would be it would look very different than if I did a 5,0 carbon nanotube and like folded that back on itself? The symmetry would be very different, right? Yeah. The size and the chirality. And yeah, the size and the chirality, which is then going to affect its conduction properties, because you're changing the alignment of these pi orbitals relative to each other, right? There are good examples of this. There's good videos online to really kind of congeal it in your mind. It might be helpful to print this out on like a transparency, or to really like start to fold these back on itself to see how this works. I can. Yep.
So are we not supposed to be able to find addresses for the atoms that are kind of off?
Let me get back to you on that. Yeah, because that is kind of disturbing.
Characterization makes sense, because you can't really fold those points back onto each other. You can't fold those like halfway.
Why not?
Yeah, are there some atoms without atoms?
Yes. Yes.
Half of them?
Yes. Half of them don't. And this system do not have an address. Yeah. So this is kind of as we go through I'm going to assign a homework today, and it's all going to be right out of the book. So if you want to get started on it, you can. We're going to talk on Monday more about how do we characterize this material. It is kind of amazing that carbon is one of the only things that exists as a 0D, 1D, 2D, and 3D system, right? Unlike semiconductors, right? We had to change different sizes, different materials, but we can't make like gadolinium or cadmium sulfide 2D. Right? We can make a 0D quantum dot, and we can make a 3D bulk semiconductor. The magic of chemistry, it just doesn't work. But you can do this in all dimensions with carbon. I don't know. I don't know. So this is what's coming, and yeah, it sounds like everybody's ready to go. So this is probably a good stopping point if you guys are leaving. Yes, yes.